we're going to hit this last part of this chapter and the next two very quick and hard. Fortunately, the last two kind of chapters are fairly straightforward. Now, in chapter 4, there's some difficulty if you have not learned well the topic in chapter 3, and especially in chapter 2, where you needed to learn to write formulas correctly. I was really stressing that. And some of you are not using the subscripts correctly on Blackboard. I really am going to dock you each time if you choose not to use those subscripts correctly. I'm happy to put another how-to video on there for you. If you'll watch it, I'll be glad to do that. But you must do so. And the number one thing to remember when you're doing this is you must focus on writing those correct formulas. And I'm going to sort of review over those again as we're doing that. But let's quickly finish chapter 3. Limiting reactants are also known as limiting reagents, and then she calls this reaction yield, and then she finishes out with types of chemical reactions, which types of chemical reactions really does not belong in chapter 3. It is really the focus of chapter 4. So I'm going to use that as a jumping off point for chapter 4. But let's begin with the last thing. When you think of limiting reactant, don't get confused with it. The best example that I know is, it's the reactant that's going to get used up. Now, let's put that into perspective. I don't know how many of you are bakers, but that's what I enjoy doing for my family. And I've baked many chocolate chip cookies, and each Sunday morning I do bake pancakes for my family. And there have been, unfortunately, in the many years, several Sunday mornings where I would get up to fix those pancakes, and alas, I'm out of eggs. And you cannot make pancakes without eggs. Or one of my kids would have had a sleepover, and we would have more kids in my house, and I would need to double or triple my recipe of pancakes, and I only had one egg. And you need one egg for each recipe of pancakes, because of course I make my pancakes from scratch. So I never have to worry too much about running out of flour. I don't have to worry too much about running out of sugar or not salt too much, but it's usually the egg that I'm going to run out of. So that is my limiting reactant. And if my kids, one of them had friends over to stay the night and I need to double that recipe, well, I better have 2 eggs or I cannot double my recipe. That would be considered a limiting reactant. It is going to limit how many pancakes that I can make. And because when my kids were small, they liked giant pancakes and they liked them to be shaped. I would shape them in whatever shape that they would ask me to. That day I was that mom. Then, they would be very large. They wouldn't be the little $half size, or, they would be large. So my recipe with my 1 egg would make 4 large pancakes. So my yield, when it's talking about reactant yield, would be 4. So 1 egg equals 4 pancakes. That's how that works. All right. So then when it talks about down here, the excess reactants are those that I have more than enough of. Now in my kitchen, I'm going to have more than enough flour, most likely. I'm going to have leftover sugar in my canister. I'm going to have leftover salt, most likely. I'm going to have leftover other things. But I'm not going to have a leftover egg. I'm going to use that up. So that's how that works. All right, I hope you have that concept down. So I'm not even going to go there. Let's just work through a sample problem and let's see how this goes. It says sodium bicarbonate, that's baking soda, and citric acid react to form carbon dioxide and other stuff. And this is the balanced chemical equation that goes with it. Here's your baking soda, 3 moles of baking soda, and 1 mole of citric acid. They react to form carbon dioxide, water, and then this other product right here. Okay? So how would you find out what is going to be your limiting reactant? Well, let's find out. An Alka-Seltzer tablet contains 1.70 grams of baking soda and 1.00 grams of citric acid. Determine which is the limiting reactant. So that's the first thing that we're going to do. So in order to find that limiting reactant, this is exactly what we're going to do. And that's all I'm going to take from this. That is all I'm going to take from this. And by the way, this is in your textbook on page 102. And I'm flipping there because I'm going to lose this screen and I'm going to go to the writing tablet now so that I can just write. So it says in the text that my balanced equation for this reaction is 3 moles of sodium bicarbonate, that's just baking soda, plus 1 mole of citric acid, that's what gives the Alka-Seltzer, I need my glasses, that's what gives the Alka-Seltzer its scent so that it doesn't taste like baking soda. That's pretty much its only purpose in life, is to make it so that it will take it and it tastes like halfway decent. And it gives off, this is what makes it fizz when you put it in the water. That's carbon dioxide bubbles, and then some extra water, and then it gives off this other product. Okay? Na3C6. Okay, so there's our balanced equation. Now, of this, it says that a single Alka-Seltzer tablet contains 1.70 grams of sodium bicarbonate. So that's exactly what I'm going to do. I'm going to find out which one of these I'm going to run out of. Okay? And I'm going to do that by saying, okay, let's say that I had 1.700 grams of sodium bicarbonate. If I had this 1.70 grams of sodium bicarbonate, how many grams of citric acid would I have to have to use it all up? In other words, if I'm talking pancakes, now I know I'm not talking pancakes here, but let's say that I were. If I had 3 eggs and I wanted to use all 3 of my eggs and make as many pancakes as I could, how much flour would I need? If it took 1 1/4 cups of flour for each and every egg, can you see with me? I could calculate out and find out how much flour it's going to take. Well, that's exactly what we're going to do, and we learned how to do this, so let's go. Our very first confactor, we want to know how many grams of that. Our very first confactor is going to be our mole-to-mole ratio based on the balanced equation. And from our balanced equation, we see that for every 3 moles of baking soda, we need 1 mole of citric acid. Okay? Now, I know what some of you are thinking. You're thinking, well, we already know we have 1.000 grams of citric acid. Yes, we do. That's how much we have in our canister, in our cabinet. We want to know how much do we need to use up every bit of baking soda that we have. How much citric acid do we need? That's our goal right here. So for every 3 moles of baking soda, we need 1 mole of the citric acid. Now I am going to take a little bit of help here because I'm going to look up these molar masses in your text. It looks them up for us and figures them up. Over here on my scratch paper, I would say, okay, for sodium, one of these times 22.99. This comes from your chart, yes. And there's, for every hydrogen, there's one of these times 1.01, and I would continue this on, okay? But I'm going to take the help that's given, and it tells me in the textbook that for every 1 mole of NaHCO3, there are so many grams. And they did this for us, and they gave us 192.12. I'm telling you, these gram formula mass ones are the most important conversion factor in chemistry. We use them all the time. Okay, and then it also tells us, oh shucks, I'm sorry guys, that is the incorrect one. That's for the other one. For this one, it is 84. .01. And then for the citric acid, it is 192.12. Okay, and once you know those things, now then you're ready to solve. And I'm going to solve always by starting with my given. I'm going to make sure I have grams of sodium bicarbonate right there. I have grams of sodium bicarbonate right here. I can circle them. Grams, grams. I also have, I can highlight this, grams of this, and I have grams of the citric acid. So I know I'm ready to solve. And I'm always going to solve by starting with my given. So for every 1.700 grams of sodium bicarbonate, and I'm just going to continue this on. Since I have this grams of sodium bicarbonate in the top, then I know that this right here is my first cofactor, and for every 1 mole of sodium bicarbonate that I need, I have 84.01 grams. And that's going to cancel. And now I have moles of sodium bicarbonate. I've used this, I'm going to cross it out. So I'm ready, since I have moles of sodium bicarbonate on top and I want to get rid of it, I know I need to use this top conversion factor because it is the one that has moles of sodium bicarbonate in it. And since it's on the top here, I'm going to put it on the bottom down here. So I'm going to say for every 3 moles of sodium bicarbonate, I need 1 mole of the citric acid. And then lastly, see that cancels with that. And then lastly, since I have this, I'm going to cross that out because I don't need it. And then that leaves me with moles of citric acid on top. Well, I don't need moles of citric acid. I need to get rid of it because I'm trying to get into grams. So for every 1 mole of citric acid, I have 192.12 grams of citric acid. And I ran out of room, but you can clearly see that that's what I have. Now I'm going to take my trusty calculator, and I'm going to type into my calculator, and I'm going to say 1.700 divided by 84.01 times 1, because this is where I am right here now. I'm saying times 1 divided by 3, because that's in the denominator, times 192.12. And then I'm going to hit enter. And I got 1.29589. And I do not have that much. Okay? I need 1.296 grams. Okay? I don't have that many grams of the H3C6H5O7. This is how much I need. I don't have that much. I only have 1.000 grams. So I'm going to run out of that. That's clear. You know, I don't have enough. I'm going to run out. Since I'm going to run out of that, that is my limiting reagent. And that's exactly what you would say. You're going to say that your limiting reagent is citric acid. That's what you would write. And then once you have your limiting reagent, now then you can see how much product you can make. Because the second part of this question says to determine, well, I'm going to tell you right now, I will not ask you question B. You would not generally, now if you were in industry, I could see some use for that, but you're not generally going to say, oh, well, let me measure how much flour I have left over. It's just not something you do. Now, if you are in an industry and you want to see how much of a product, how much of a reactant you have left over to see if you can make something else, let's say, then you might do that. But part C for sure you will have to do, because it's asking you how much product can you make. So it's asking you, so I'm going to focus on part C now, how much carbon dioxide forms. Well, what's going to determine how much carbon dioxide forms? The citric acid. The citric acid is what determines how much carbon dioxide forms. So you're going to do this exact same process again, but you're given, you have two numbers in the given. You have 1.700 grams of baking soda and 1.00 grams of citric acid. Which one's going to be your given? Your given's going to be the one you run out of. Okay? So you're going to do this exact process again. Only this time, your given is going to be for sure your citric acid, because it is your limiting reagent. So I'm going to use 1.000 grams of my citric acid. Now, your textbook did this a little bit different. I really like my method better. I think it's easier to follow. I think it makes more sense. So that's on you, however you would like to do it. I think it flows better. With this way, if you had chosen to use the other one, if you had chosen to start with citric acid, then you would have gotten, for your answer, you would have gotten a number that's less than 1.700 grams of baking soda. And so you would say, oh, I have enough baking soda, so I'm not going to run out of it. So I'm still going to run out of citric acid. I hope that makes sense to you. All right, so we are unknown here because we're doing part C. This is part C. Oops. Our unknown. This is part C again. our unknown is how many grams of CO2 can form. This is the exact same problem. This is the exact same balanced equation. What do we care about in our balanced equation this time? We only care about two things. So for our factor, our first conversion factor, it is going to be for every 1 mole, because all we care about is the citric acid and the CO2. So go look on page 102, look at that balanced equation, and you can see that the recipe or the equation says for every 1 mole of citric acid, you can make or produce 3 moles of carbon dioxide. Okay? And now then you ask yourself, am I ready to solve? Is that all I need? And if it asked you for moles and it gave you moles, then yes, you'd be ready to solve. But it didn't. It gave you grams. And because it gave you grams right here, you are not ready to solve. You've got to get these grams, and you've got moles right now in your factors. So how do you go from moles into grams? Well, you use your molar mass. You use that 1 mole of H3C6H5O7 equals so many grams of that. I'm not going to write that formula again, but it would be H. I'm going to run out of room. And remember, this one was 192.12. Now, if they don't give you that, you're going to have to say, use your periodic chart and do that. And 1 mole of CO2 equals blank grams of CO2. Now we can quickly do this. Carbon, there's 1 of them times from the periodic table, that's 12.01. And oxygen, there's 2 of them in our formula. Each one has a mass of 16.00. That's from the chart. So that's 12.01 plus 32. 2 times 16 is 32. So that's 44.01 grams. Okay? That's how those came from. Now we're ready, because now we have grams of CO2, grams of CO2. We have grams of citric acid, grams of citric acid. So we are ready to solve. And we're going to always start with that given. And since we have grams of our given on top, grams has got to go on the bottom. So this 192.12 grams of H3C6H5O7 in 1 mole. That's going to go on the bottom. And now I'm going to run out of room because of that long formula again. Okay, I've used this factor now. Now then, I have moles of citric acid. I'm going to put Ca for citric acid. I should have done that a long time ago. And for every 1 mole of citric acid, there are 3 moles of carbon dioxide. And then for every 1 mole of CO2, there's 44.01 grams. And so then you're going to put that in your trusty handy dandy calculator. And you're going to say 1.00 divided by 192.12 times 3 times 44.01. And you should get 0.687. And we have 1, 2, 3, 4. We have 4 sig figs in our given. So that's what you should report in your answer. And I got my answer to be. I'm going to write it right down. I don't know where I'm going to write it. I ran out of room. 0.6872 grams. That's what I got. This is my final answer. Okay? Alright. That's called your theoretical yield, because that's how much you should be able to make. Theoretical yield. I'm going to do a short video next.